We want to evaluate the given line integral along the curve C, where C is the arc of the curve y equals e raised to the power of x for x greater than or equal to 0 and less than or equal to 3. And notice how in this example, the line integral is written in differential form, so our process will be a little bit different. We want to begin by parameterizing the curve C, meaning we need to write parametric equations that will trace out the curve C. So if we have y equals e to the x over this interval, the easiest parameterization is probably going to be let x equal t, or x of t, be equal to t. So if x is equal to t, we can write y, or y of t, as y of t equals e raised to the power of t. And because we have x equals t, the interval for t is also going to be the closed interval from 0 to 3. And we're also going to need x prime of t and y prime of t, so let's go ahead and find those now. X prime of t is equal to the derivative of t with respect to t, which is 1, and y prime of t is equal to the derivative of e to the t, which is just e to the t. Now looking at our notes below, because the given line integral is in differential form of this form here, for the next step, let's write this as two separate line integrals in this form here. So the given line integral is equal to the line integral along the curve C of x integrated with respect to y, plus the line integral along the curve C of y integrated with respect to x. Now for our next step, looking at these notes here, we'll write the integrand function as a function of t using the parametric equations, and then differential x is equal to x prime of t dt, and differential y is equal to y prime of t dt. So for the first line integral, we'll have the integral of, well, x is equal to t, so we'll have t, and again, differential y is equal to y prime of t dt, which should be e to the t dt. The limits of integration for t are going to be from 0 to 3. Then we'll have plus the integral of y, which is equal to e to the t, and then differential x is equal to x prime of t, which is equal to 1 times dt, so we just have dt. And limits of integration for t, again, are from 0 to 3. Now let's evaluate these on the next slide. In order to evaluate this line integral, we'll have to perform integration by parts, and I've included the formula here below for review. So applying integration by parts, let's let u be equal to t, and therefore differential u is equal to 1 times dt, or just dt. So if we let u equal t, then e to the t dt would be equal to dv. So if dv is equal to e to the t dt, we need to integrate both sides of the equation to find v. Well, the integral of e to the t with respect to t is just e to the t. So now applying integration by parts, we're going to have uv minus the integral of v du. Well, u times v is t, e to the t. And then we have minus the integral from 0 to 3 of v du, which should be e to the t dt. And we still have plus the integral from 0 to 3 of e to the t dt. Notice here these integrals are opposites, and therefore this sum is going to be 0. So we just need to evaluate this to find the value of the line integral. So when t is equal to 3, we have 3 times e raised to the power of 3 minus, when t is 0, we have 0 times e to the 0, which would just be 0 times 1, or 0. So the exact value of the line integral is 3 times e raised to the power of 3, which as a decimal is approximately 60.2566. I hope you found this helpful.